may seem to you that I have developed an unhealthy obsession with the Fresnel integrals, but that's not the case. The case is, in fact, that the Fresnel integrals are extremely cool to evaluate using various techniques. Now, previously, I evaluated them using Feynman's technique of differentiating under the integral sign, using the Leibniz rule, and before that, I evaluated them using basic complex analysis, and you don't even need contour integration. You can find a much more elegant solution by using Euler's formula and drawing some parallels with a Laplace transform. I've linked both those videos in the description below, the one involving Feynman's technique and the one involving just basic complex analysis. And that solution, the one involving basic complex analysis, is in fact the most elegant solution, but using Feynman's technique, and in this video I'm going to be using the Laplace transform to sort of integrate under the integral sign. And both these techniques are extremely cool, if not as elegant as the technique using complex analysis. So in this video we need two tools. We need the Laplace transform and we need Euler's formula, which states that if you have e to the I times t, where I is the imaginary unit, this equals the cosine of t plus I times the sine of t. Just as before, we can connect these two integrals using Euler's formula by defining e to the ix squared, because this is in fact equal to the cosine of x squared plus I times the sine of x squared. So in order to evaluate the two Fresnel integrals, I will be evaluating the exponential function here, e to the ix squared. So we're integrating e to the ix squared from negative to positive infinity with respect to x. And we're going to use the Laplace transform here. So let's define an integral function I of t. Now, this function is not as extravagant as the integral function defined in that Feynman integration video. So here we have I of t defined as the integral from negative to positive infinity of e to the ix squared times t. So we've introduced the parameter as part of the argument of the exponential function. And now to apply the Laplace transform to the function I of t. Now the Laplace transform equals the integral from 0 to infinity of e to the negative st times I of t, integration with respect to this parameter t. Now expanding this function I of t in terms of its integral definition, we have the integral from 0 to infinity of e to the negative st times the integral from negative to positive infinity of e to the ix squared t, integration with respect to x, and outside we have this integration with respect to t. Now notice first up that the exponential term e to the negative st is independent of x, so you can slip it into this x integration. So you have the double integral from 0 to infinity and negative to positive infinity of e to the negative st times e to the ix squared t, integration first with respect to x and then with respect to t. As you would expect, it would be quite useful if we can switch up the order of integration. And for that we have to consult Fubini's theorem. Now, Fubini's theorem states that if the function you're integrating, the function of the two variables in this case, x and t, if the function you're integrating is continuous over the region on which you're integrating. So if continuity over our region is satisfied, then yes, you can switch up the order of integration. So thank you, Top G Fubini. We can now switch up the order of integration, and we're integrating now first with respect to t and then with respect to x. And we have the function e to the negative st times e to the ix squared t. And this is the cool stuff, because what you have here, if I just isolate this t integral, what you have here is the Laplace transform of e to the ix squared t. And x is a constant in the t world anyway. So you can apply the Laplace transform. This integral, the one underlined in orange, reduces to this Laplace transform, which according to our table is going to give us 1 by s minus this constant term that t is being multiplied with. So this is what your integral now looks like, and we're completely in the x world, meaning s is a constant. And you can expand this using the complex conjugate to help separate the real and imaginary parts. So multiplying upstairs and downstairs by the complex conjugate of the denominator, and then using that algebraic identity of x plus y times x minus y equal to x squared minus y squared, we now have the integral from negative to positive infinity of s plus ix squared divided by s squared plus I squared x to the fourth power, and I squared, sorry about that, you had s squared minus I squared times x to the fourth power, and I squared is just -1, right? So two negatives will cancel out, and now you have two integrals, one for the real part and the other for the imaginary part, which shows that we're doing something right. We're doing something right, or we haven't made any horrific mathematical mistakes so far, because after all, the Fresnel integrals, one is the cosine, which is the real part, and the other is the sine term, which is the imaginary part. So it's nice that they're separating out so well. Integral from negative to positive infinity, x squared by s squared plus x to the fourth power. And the title of the video is by no means any disrespect towards flammable maths. I, in fact, watched his video on solving the Fresnel integrals using the Leibniz rule, and there was one small mistake towards the end that he corrected in a follow-up video, which was pretty cool. And Flammable Maths is actually my favorite math channel on YouTube. And in the recent past, he hasn't been uploading those kind of really hard integration problems or tough mathematics as before, but the legacy still lives on. I mean, I hope he gets back to that really fun, hard mathematics that he was uploading. And even if you look at his videos from like 3, 4, even 5 years back, the content is just amazing. I mean, definitely my favorite mathematics YouTuber, although most most math YouTubers are just solving those clickbaity or interesting looking algebra problems and stuff like that. But he was actually getting his hands dirty with really hard math problems, especially those early videos on integration. All of that is extremely awesome. And he even has these playlists on Laplace transforms, deriving them, etc., etc. His analytical mechanics playlist is also pretty damn cool. So yeah, this is by no means any disrespect to my favorite YouTuber. No means at all. And I'm not sure how you're doing these days, but I remember you being sick. So Flammy, I hope you're doing better now, and I wish you the best of health. And get well soon and get back to some really awesome math stuff, man. Get back to it. His video was titled An Insane Approach to the Fresnel Integrals Without Complex Analysis. Yeah, something like that. But in my opinion, this is even cooler. I mean, applying the Laplace transform to the complex exponential function is even cooler than even applying the Leibniz rule to the Fresnel integrals. And although Feynman's technique is actually my favorite integration technique, and it is hands down the coolest way to integrate, but I think this is one of those cases where the Laplace transform actually looks even more awesome than Feynman's technique. Anyway, so this is what we have right now. We have the Laplace transform of I of t, and we've separated it into real and imaginary parts. And now to make life easier, I'm going to perform a substitution where we let x equal u times the square root of s, which implies that dx equals square root s times du. We're in the x world now completely, so the s terms are just constants anyway. So yeah, that's pretty helpful. So under the substitution, the Laplace transform of I of t equals the integral from negative to positive infinity, and this s here is just a constant, so pull it out. The differential element up here, square root s du divided by, now you have s squared plus, what's x to the fourth power? Well, accordingly, this should be u to the fourth power times x squared. So you can actually factor out this s squared term. So you have 1 plus u to the fourth power. And for the other integral, you have the imaginary unit I. And up here, you have x squared, correct? So x squared would be u squared times s. So u squared, s outside, differential element, again, it has the square root term, the square root of s. So I'm gonna have to make better use of space. So s times the square root of s. And as before, you can factor out s squared from the denominator. So you have some stuff canceling out outside, which is quite nice. So outside each integral, you now have 1 by s to the 1/2. And these two integrals here, I've evaluated them in a previous video, and these two integrals are equal, and they evaluate out to pi by the square root of 2. Link in the description below. However, in that video, I'm integrating from 0 to positive infinity. And so in this case, when you're integrating from negative to positive infinity, you have to double the result, because these are even functions, right? The integrands are even functions. So plus the imaginary part times the imaginary unit times 1 by s to the 1/2, or the square root of s, times this integral, which is also pi by the square root of 2. So this is the Laplace transform of I of t. But now I want to recover back my integral function, and for that I have to select a nice color and apply the inverse Laplace transform. Now, the inverse Laplace transform, like the Laplace transform, is a linear operator. So you can take the Laplace transforms separately, plus I times inverse Laplace transform of exactly the same thing, pi by square root 2 times 1 by s to the 1/2. Now for some manipulation, you can write pi as the square root of pi times the square root of pi, right? So what I'm going to do here is take square root of pi outside along with this 1 by 2 factor. So outside each inverse Laplace operation, you have a constant multiple of square root pi by 2, correct? And inside you still had 1 square root pi left, and square root pi is the gamma function of 1 by 2. So I hope you were following me while I was doing all that stuff here. So we have gamma functions, gamma 1 by 2 by s to the 1/2. So in your table of Laplace transforms that you've just Googled, you see that the inverse Laplace transform of this term here, gamma 1 by 2 by s to the 1/2, is in fact t to the negative 1/2. So this is all pretty cool. And we have, again, t to the negative 1/2, square root pi by 2. So this is the integral function I of t. This is what it evaluates to. And we were interested in the case where t equals 1, right? Remembering that our integral function I of t is in fact the integral from negative to positive infinity of e to the, not negative, it was a positive term, ix squared t dx. So we're interested in the case where t equals 1. So in case t equals 1, that means your integral, which is the integral from negative to positive infinity of e to the ix squared dx, equals square root pi by 2 plus I times the square root of pi by 2. And all that's left now is to separate the real and imaginary parts on the left-hand side. So you get the integral from negative to positive infinity of the cosine of x squared equal to the integral from negative to positive infinity of sine x squared, and all of this equals square root pi by 2. So yeah, that was awesome. Definitely awesome. And I still believe the most elegant way of evaluating these Fresnel integrals is using basic complex analysis. But this is still pretty cool. This is still pretty cool. And I think out of all the ways I've evaluated them, including contour integration, although I haven't made a video on it, on using contour integration for these integrals, I think that this is definitely the coolest approach. So anyway, be sure to like and subscribe. Thank you. See you next time.